Hello, I'm Gary Bradsky. I'm doing this by video because I tested positive for COVID. I'm okay so far. So I'll be discussing OpenCV and the future of computer vision. So a little intro to OpenCV. It's both a computer vision library and a nonprofit foundation, as we state here. It's the world's most popular library. It gets about 200,000 downloads a day, mostly through Python. It's mature. It started 20 years ago, mostly in C++, but has interfaces in Python, Java, JavaScript. It's large and comprehensive. It's widespread, has a large active community, and it tends to be decently efficient. So the areas that the library covers are, as you can see, image processing, geometric transforms, image fitting, optical flow, segmentation. On the bottom, calibration and geometry, SLAM, depth, deep learning. It does inference very efficiently, especially on edge architecture and computational photography, and includes the supporting data structure and other interfaces to that. So this is just a look at our sponsors. We have a lot of large and smaller corporations that we work with. So OpenCV has a commercial side separate that does contracting. So here you can see some of the things that we've done, a lot of medical work, sports work, AR, VR, and a number of things like shopping and grocery checkout shopping and other things. We also partner with hardware, so this is a smart camera, the OpenCV AI Toolkit. It's a depth camera that's smart. It has 4 teraflops of processing on it, so it does stereo and deep nets on it, and this is used quite extensively. We also offer this marketplace of models, many of which work on the Oak, and they tend to be optimized and highly functional. So there's a little video showing what some of the things that are being offered, and there's a little representation of some of the things on the left. Okay, OpenCV is used all over the place, as I said. It's got many millions of downloads, 200,000 downloads a day, at least for Python and BuildBots. And so we'll cover some of the uses, just a few, in video and broadcast first. So on the left, you can see image stabilization. On the right, very robust trackers that we have. So tracking objects and tracking for stabilization here. And I'll just let this go a bit to watch. Anyhow, moving on. We also do things like colorization, as you see the original video on the left and the colorized version on the right that's being done in real time. Here's segmentation. Above is someone in their living room, and then they're cut out and put in a scene. Below is driving and through streets, so for automotive. Some other things we did in broadcast. Here's stable tracking on the left, that from a drone, and on the right was some movie work. You can see, can overlay very stably a fictitious car, so that car isn't there. It's just a dune buggy, and this was done on stage in the movie form. And Super Bowl stadium footage is on left. So very stable tracking that we're able to do things with. So here's some pictorial tools that are useful. There's a lot of stuff, factorizing, lighting from surface. Below that is color calibration, Macbeth charts, and high dynamic range. Other things are, as we've seen, colorization or color transfer. That right, color constancies, so trying to keep a constant color in a scene. And then some fun stuff like tilt shift photography to make things look like a toy model. Here's cartoonization, super resolution. As a small resolution image is blown up, you can see the blur, but it's restored on the right, and this can be done in medical imagery as well. OpenCV is used extensively in robotics. So here's some of the list. It's used in industrial pick and place, it's used in logistics, it's used in eyelash placing. It kicked off autonomous driving. It's used in factories on to home vacuum cleaners. So this is a use we did, Industrial Perception. It's a company that sold to Google, and here, just for fun, we actually did this for Larry Page's birthday party, where we were handing out party favors using this. OpenCV was instrumental in autonomous driving, and this is a DARPA Grand Challenge where Stanley, our team, won the $2 million prize and really kicked off autonomous driving. So here you see BOSS, the CMU, is starting off, and that's followed by Stanley. Just skipping ahead, there's the race as it went. This is when we were passing BOSS. You can see the 3D LiDAR scan, and then going down the mountain pass and on to the finish line as you see it coming. So here's some more modern uses in autonomous driving. So lane detection, car detection, sign detection, pedestrian detection, stoplights. And recently we've been using this in agriculture. So on the left is road detection and path planning, the path to follow, people detection. And on the right you see a robot that's following a person for, say, harvesting. They can carry things on it, and then the person can walk down the row. And we'll just show a little bit of this as we speed it up. So it follows him wherever he goes and stops when he stops. Okay, OpenCV's use in, or Vision's use in medical. So some of the things that have been done are skin detection for treatment and conditions. This is a summary of a lot of things that have been done in vital sign detection by a regular camera, blood flow, again by a regular color camera, and we got first place in a 3D tomography segmentation in 2020 contest. So other things that can be used, this is body tracking. This is also used for sports, but any motion and identifying body parts. So it's pretty robust. This is a robotics application in eyelash extension. So this is someone's eyelash, and it's epoxying new eyelashes onto it. That's by Loom. So here's Odena is doing using OpenCV for pathology detection, as you can see. So moving on to new areas. So here's a list of emerging areas. So self-supervised learning, use in driving, understanding, autonomous driving. Deep vision on edge devices, so we saw the OAK-D camera already. Predictive 3D solutions to protein folding, that's AlphaFold, upper right. Growing use in agriculture, I already showed that. This is FarmNG, the tractor, for example. Use in medicine, below center is Gauss surgical blood loss tracking. And generative models for art and description, that's bottom. And also for understanding causality, which I'll talk more about. So first, self-supervised learning. Here's two examples of what is done. On top right, we mask out a lot of the image and ask the network to predict the rest and iterate on that at different images. So it learns to the structure of images. In the bottom, we see we get a bunch of images and do transforms of them, but in the middle of that network, it's focused on learning the same representation for this object. In this case, it's a dog, and then you'd feed other objects in. And so it learns this representation to be the same for each object that it happens to pass. Here's an example of deep generative models. So, for example, upper left, it's asked to draw a cat, the same cat in a drawing manner, and the network generates that. Bottom is a chair in the shape of an avocado, and that's generated by the network, and so on. This is a neural radiance field, so it learns a generative compact model of an object, and this is using the OAK-D camera. This was for a contest we ran, and this is it. It's just a Lego set, spinning object. It's learning a few views, and then it learns to generate this object from any view. So almost none of these views have been seen before, and it's just generating because it has learned a full representation. The network itself represents this object. And you could see possible uses with speeding up MRIs by being able to capture basically the whole thing in much fewer views. So lately, and to me most exciting, is the learning causal models. Those are descriptive, what happened, explanatory, why did it happen, predictive, what will happen next, and counterfactual, what would happen if. And so there's a lot of work going into this. To me, this is getting closer to real AI, and so you can see a causal model on the right that's learning these things about this physics scene. And the results, as you can see in yellow, are much better. Descriptive has already been done pretty well, but explanatory, predictive, and counterfactual are much less progress, but this model's done substantially better. So this kind of thing is starting. So I'm going to end this talk with talking about causal simulation as it pertains to general AI through vision models. Okay, so we ourselves have a causal model of the world. We don't perceive the world. The analogy is, say, on your computer user interface. For example, there's a trash can there, but I'll tell you, there's no real trash can inside your computer. And physicists will say, you're right, the trash can is made up of quanta, pixels. But that's wrong. The real reality is this strange von Neumann architecture beneath it all. What's true is we have a causal model, so if you move things into that trash can, they'll be deleted. This is an analogy for our own perception and any perception. And so here's an example. It's a famous Conixa triangle. So you have illusory completion of the boundaries if you're looking at this from the right distance. And the brain is imputing this causal model that it's actually in 3D and the triangle is floating above these complete circles. And that's how this illusory contour is inferred from vision. So we're not seeing the world, we're seeing a model of the world. It's a causal model. And again, this is simple when you think left about just points of view of two objects in 3D. You can see it, the pictures below show you get a completely different percept, yet we perceive it the same. And so on right, there's a famous, this is in Stanford's Hall, a famous illusion. So you can see when something is seen in 3D versus the actuality, the scene looks normal to our view, but when you move the guy in back forward, it looks very strange. So the outer world is actually a causally simulated inner world. The outer world exists, whatever it is. We create a causal model of it that's much more sparse. And so, here's some drawings by my friend of this. So the simulation is causally sufficient, but it's not true. It doesn't contain the whole world like any model. And so I like to say, what is beyond the sky, right? Above you, what's beyond the roof? Well, it's the inside of your skull, and this is pretty obvious on reflection. So we live in our own simulation bubbles. I like to say when you wake up, the dreams don't end, they just connect to a data source. And so we're simulating the world kind of like we live in our own matrix, if you saw the movie. But it's not a machine, it's our own perceptual apparatus. So we simulate also our social selves and the social dynamics. You'll see this in the dream when you meet people, and often there's things you're discussing, and in fact, you simulate yourself also. So when we apply a social simulation of others to our model of ourself, then I'm suggesting that that's kind of the pathway to self-awareness or consciousness. And that's where I end this talk. Hopefully I'll be around for questions.